Think about the last time you took a transatlantic flight. Like maybe you arrived an hour early, or perhaps you hit this incredibly rough patch of turbulence out of nowhere, spilling your coffee everywhere.
Oh, yeah, the dreaded sudden coffee spill. We've all
All
been there.
right. Well, up to about 5 miles above your head, there is an invisible river of air that's basically dictating that entire experience.
And it is moving fast, like sometimes exceeding 250 miles per hour fast.
Yeah, which is just wild to think about. So today we are taking a deep dive into the jet stream. These are the high-speed atmospheric superhighways that dictate your local weather, steer massive hurricanes, and honestly currently sit at the absolute center of this fierce scientific debate about the future of global climate.
It's a massive topic. It really touches almost everything about our daily environment.
It does. Okay, let's unpack this. I mean, how do we even know there is this massive raging river in the sky when we look up and see, well, absolutely nothing?
That is the million-dollar question,
Right.
because it required this really bizarre historical puzzle to finally visualize it. We're talking a timeline spanning massive volcanic eruptions, early global aviation, and even an invented language.
Right. An invented language.
Yeah, I'll get to that in a second. It's wild. But the initial inkling actually came from an American professor, Elias Loomis, way back in the 1800s.
Okay, so a long time ago.
Right. He mapped out the behavior of major storm systems moving across the U.S. And he realized that the physics of these storms just didn't work unless there was some powerful high-altitude current constantly pushing them from west to east.
But I'm guessing he couldn't exactly prove it back then, right?
Exactly. It remained this unproven hypothesis until a totally catastrophic event gave the world essentially a giant tracer die.
Oh, right, the 1883 Krakatoa eruption.
Yes, Krakatoa.
Because that was an earth-shattering explosion over in Indonesia. It just injected these unfathomable amounts of ash and dust straight up into the upper atmosphere.
Right, and suddenly, weather watchers globally had a visual marker in the sky. They tracked this volcanic debris as it literally circled the globe for years.
And they called it the equatorial smoke stream, didn't they?
They did, yeah. So they gave us the visual proof of high-altitude movement. But the actual scientific quantification of the jet stream, that suffered a brilliant but kind of tragic translation error.
Ah, this must be where the invented language comes in.
You guessed it. So in the 1920s, you have this Japanese meteorologist named Wasaburo Oishi, and he started meticulously tracking these pilot balloons. They're known as Piebles, right near Mount Fuji.
Okay, so he's sending up weather balloons.
Yeah, and recording hard data on these incredibly fast, continuous high-altitude currents. I mean, he'd cracked the code. He found the jet stream.
Wow. So why didn't the whole world know about it immediately?
Because Oishi desperately wanted his discovery to bypass national barriers. He wanted to reach a truly global scientific audience. So he chose to publish his groundbreaking findings entirely in Esperanto.
Oh, man. He used a language explicitly designed to bring the world together.
Yeah. And as a direct result, almost no working scientist could actually read it.
That is just a staggering historical irony.
It really is. I mean, he discovers this global sky freeway, and the knowledge is essentially lost because of his formatting choice.
Wow. So when did we actually figure it out on a global scale?
Well, the world had to wait for aviation technology to physically bump into it. In the 1930s, you have the American pilot Wiley Post, the guy famous for being the first man to fly solo around the world.
Right, right.
Well, he developed a pressurized suit, and this allowed him to fly way up there, above 20,000 feet. And up there, he noticed this massive discrepancy. Like his ground speed was wildly exceeding what his airspeed indicator told him his plane was actually doing.
So he had accidentally merged onto the superhighway?
Exactly. He was riding a current of air so fast it was physically carrying his aircraft across the map faster than his engine ever could.
That's incredible. But the phenomenon only became universally recognized during World War II, right? Like out of sheer military necessity.
Yeah, the scale of military aviation during the war really forced the issue. You had American bombers flying missions over Guam, and suddenly they hit these invisible walls of wind.
And we're talking, what, 100+ mile per hour headwinds?
Oh, yeah. I mean, winds so strong they'd practically hold a massive bomber suspended in place in the sky, or tailwinds that would blow them completely off target. There was actually a meteorologist named Reed Bryson on those flights who documented it.
Wow, that must have been terrifying for the pilot.
Oh, absolutely. But it finally brought the phenomenon into the mainstream. A German meteorologist, Heinrich Silkhoff, he actually gave it a lasting name in 1939. He coined the term Strahlströmung, which literally translates to jet current.
Okay, so now that we've mapped out how we found it, we really need to establish the mechanics. Like, what is it?
Right, so basically the jet streams are these fast-flowing, narrow westerly air currents, and they're specifically located near the tropopause.
The tropopause. That's that boundary layer about 30,000 feet up, right? For about 9.1 kilometers.
Spot on. Yeah, it's the physical ceiling between the turbulent troposphere, which is where all our weather happens, and the calm layered stratosphere above it.
And don't we have, like, a couple of main jet streams we deal with?
We do. We operate with two main sets in both the northern and southern hemispheres. You have the polar jet, which flows lower in the atmosphere and is significantly stronger. That one snakes its way between 30 and 60 degrees latitude.
Okay, and the other one?
That's the subtropical jet. It's situated closer to the equator, around 30 degrees latitude. It runs higher up and is generally much weaker than the polar jet.
Got it. So what's the actual engine driving these colossal currents? Because it has to be a massive force.
It is. It's driven by the stark temperature difference between the equator and the poles. Climatologists call this the thermal wind relation.
Okay, so the equator receives direct, intense solar heating, right? Creating warmer, expanding air. And the poles just remain freezing and dense.
Exactly. And when you have two radically different temperature zones like that, you create a massive pressure gradient. The atmosphere basically inherently wants to equalize that pressure.
Wait, let me pause you there. If you drop a dense mass of cold air right next to a less dense mass of hot air, wouldn't the cold air just want to rush straight toward the hot air to balance things out?
Yeah, it absolutely does.
So shouldn't the wind just blow directly from north to south? Why is it blowing from west to east?
That is a great question. And it would blow straight north and south if the Earth were a stationary object.
Ah, but the Earth is spinning.
Exactly. It's a rotating sphere, which introduces the Coriolis force. Because the planet is spinning, that air that's trying to move north or south gets severely deflected. In the northern hemisphere, it gets deflected to the east.
Oh, okay. So this sharp temperature gradient creates the initial rush of air, and then the sheer rotational spin of the Earth bends that rush into a tight, continuous band.
You've got it. Blasting from west to east. And that spherical shape creates another crucial dynamic, too. Because the Earth's rotation speed isn't uniform.
Right, it's spinning much faster at the equator than it is near the poles.
Exactly. Which means the Coriolis effect actually changes depending on your latitude.
Which perfectly explains why the jet stream doesn't just flow in a perfect, rigid circle.
Right, because that rotational deflection alters as the air moves north or south. The river of air buggles. It, like, snakes and meanders into these massive sweeping loops.
They're called Rossby waves, right?
Yes, Rossby waves. And these enormous atmospheric meanders are basically what physically drag high and low pressure weather systems across our continents.
Wow. Okay, so understanding those sheer physical forces really completely changes how humans have learned to exploit the jet stream.
Oh, heavily. I mean, commercial aviation relies on it daily. Airlines actually build complex algorithms to route flights directly inside the jet stream to save massive amounts of time and fuel.
Which is wild. Like, Pan Am pioneered this way back in 1952. They dropped the flight time from Tokyo to Honolulu from a grueling 18 hours down to just 11.5 hours, simply by riding the current.
It's basically a massive tailwind. And fast forward to February 2024, the jet stream was ripping across the Atlantic with such intense ferocity that commercial passenger jets were pushed to ground speeds exceeding 800 miles per hour.
Over 800 miles per hour. That means relative to the ground below them, they were traveling faster than the speed of sound.
Yeah. But turning a commercial aircraft into a bullet comes with incredibly violent risks, too.
Because you're navigating a narrow ribbon of air moving at like 200 miles per hour, surrounded by ambient air that's moving at a fraction of that speed.
Right. The boundary between those air masses isn't a solid wall.
Yeah.
It's this brutal friction zone, creating intense vertical and horizontal wind shear.
It's kind of like imagining two massive conveyor belts side by side moving at vastly different speeds. The air along that border just tumbles and rolls, creating these chaotic, invisible eddies.
Yes, exactly. This is what we call clear air turbulence, or CCAT, and it is incredibly dangerous because it occurs without any clouds or storms.
Meaning standard weather radar absolutely cannot see it, because radar relies on bouncing signals off water droplets, right?
Exactly. No water droplets means pilots are flying completely blind into this shear zone, which sits mostly on the cold air side, just under the axis of the jet.
That's terrifying. Like the tragic 1997 incident with United Airlines Flight 826, where sudden clear air turbulence caused a fatal plunge. It's a really stark reminder that this invisible river has devastating rapids.
It really does. And, humanity has also attempted to turn those atmospheric rapids into weapons.
Oh, you're talking about the Fugo balloon bombs.
Yeah, during World War II, Japan engineered this campaign. They launched thousands of these cheap incendiary-carrying balloons high into the atmosphere, relying entirely on the winter jet stream to carry them across the Pacific Ocean.
And just drop them onto North America. I mean, that is the atmospheric equivalent of dropping a message in a bottle into an ocean of air.
An ocean of air, yeah.
Yeah.
And hoping it strikes a specific target on another continent entirely.
It's a terrifying application of fluid dynamics, really. I mean, while it was largely ineffective militarily, I think it caused 6 deaths and sparked some unfounded fears of biological warfare. It fundamentally proved the jet stream was a physical bridge connecting continents.
Absolutely. Though today, the ambition to harness that raw kinetic energy has shifted heavily towards survival rather than warfare.
You mean wind power?
Yes. There is an active, heavily contested scientific debate right now regarding jet stream wind power. Some researchers look at the sheer velocity up there and just see the ultimate renewable energy source.
But the disparity in the calculations is wild. I mean, you have a highly optimistic study by Archer and Caldera, and they calculate that Earth's jet streams contain roughly 1,700 terawatts of power.
Which is a staggering number. To put that scale into perspective, tapping just 1% of that would solve the entire world's current energy demands.
But then you have a counter-study by Miller and his colleagues, and they argue it could only yield about 7.5 terawatts, making it completely unviable as a major power source. How can scientists be off by a factor of over 200? Are we looking at a silver bullet for the energy crisis or a complete pipe dream?
Well, the discrepancy really comes down to the physics of extraction. The optimistic study simply measures the total kinetic energy moving through the sky, just raw numbers.
Okay, and the pessimistic study?
They apply actual fluid dynamics. Think of it like putting water wheels into a narrow, fast-flowing creek. If you put in a few, sure, you generate power. But if you fill the entire creek with massive water wheels, you create so much drag that you effectively dam the river.
Oh, wow. So you destroy the very flow you were trying to harvest.
Exactly. Putting thousands of giant turbines in the jet stream could fundamentally alter global atmospheric circulation.
Which brings us to the most critical function of the jet stream for you listening. It is the ultimate weather maker. Altering its circulation isn't just an abstract physics problem. It determines whether your local farms flood or turn to dust.
Very true. Let's look at the El Niño Southern Oscillation, or the ENSO cycle. When the Pacific Ocean temperatures shift during an El Niño, it physically bullies the jet stream into a new position.
Basically pushing it around.
Yeah. During El Niño, the polar jet stream intensifies and drops further south. And this specific alignment acts like a fire hose, blasting California and the Gulf Coast with increased precipitation while dumping heavy snow across the southern Rockies.
And then, if you flip the ocean temperature to La Niña, the jet stream retracts northward. Suddenly, the Pacific Northwest is getting soaked, while the southern states bake in hot, dry conditions.
And when these shifts persist, they can literally rewrite history. Climatological data strongly suggests that a weakening and southward diversion of the jet stream in the 1930s systematically starved the American Midwest of its usual rain systems.
Wow, serving as the direct mechanical cause of the devastating Dust Bowl drought.
Exactly. But it can also act as a shield. Strong wind shear from the jet stream regularly tears the tops off, forming hurricanes, like it did protecting Hawaii from Hurricane Flossie back in 2007.
Okay, here's where it gets really interesting and frankly kind of contentious, which leads us directly into the most complex, high-stakes scientific debate currently happening in climatology.
Oh, definitely. Because we know the jet stream dictates global weather, and we know its engine is the temperature gradient between the equator and the poles. But that engine is currently undergoing a radical change due to Arctic amplification.
Right. The Arctic is warming at a staggering pace. Since 1979, the Arctic Circle has warmed nearly 4 times faster than the global average. In specific hotspots, like the Barents Sea, it is warming up to 7 times faster.
And just to be clear, both sides of the scientific community universally accept this data. The fierce debate lies in what this melting Arctic actually does to the mechanics of our high-altitude rivers.
Exactly. So let's impartially break down the 2 main competing hypotheses.
Let's start with hypothesis A, which is most notably championed by climatologist Jennifer Francis. Her argument relies directly on the thermal wind relation we talked about earlier.
Okay, so if the jet stream speed is dictated by the extreme temperature difference between the hot equator and the freezing Arctic, a rapidly warming Arctic means that temperature gap is shrinking.
Right. And I can see where this physics equation leads. If you lower the temperature gradient, you lose the pressure differential.
The jet stream loses its fuel.
Yes. It weakens, slows down, and its path gets, well, wobblier. Those massive Rossby waves we discussed, the snaking meanders, they get much deeper. And because the wind is slower, those waves stall out in place.
And here is where the mechanics of extreme weather kick in. I mean, think of a strong, fast jet stream like a rigid fence spinning around the top of the globe, locking the freezing polar vortex air tightly over the Arctic.
But as that temperature gradient drops, that tight fence morphs into a lazy, meandering river. When it meanders deeply to the south, it breaches its banks, dragging freezing Arctic air thousands of miles equatorward.
Which perfectly explains a paradox that often trips people up. Because if the Arctic is getting hotter, shouldn't we experience milder winters?
That seems like we should, right? But the mechanics of hypothesis A explain why a warm Arctic results in a catastrophic polar vortex freeze in Texas, like those massive power grid failures in 2014 and 2021.
The cold air didn't disappear. The fence holding it back simply broke, spilling the freezer into the living room, so to speak.
That's a great way to put it. And furthermore, because these wobbly waves move so slowly, they create atmospheric blocking. Weather systems just get stuck in place for weeks.
Leading to persistent extreme events, like the stagnant 2018 European heat wave or the unrelenting rains that caused the 2010 Pakistan floods.
Exactly. So that is hypothesis A, is a mathematically sound, deeply concerning hypothesis. But clashing against it is hypothesis B, which represents a really robust body of counter-evidence.
And this relies on massive long-term data sets and state-of-the-art modeling.
Yeah. To isolate these variables, climatologists use tools like the Polar Amplification Model Intercomparison Project, or PAMP for short.
And these are incredibly complex simulations designed to look specifically at sea ice decline, essentially separating it from the chaotic noise of general global weather, right?
Right. And the PMP models suggest that the loss of Arctic sea ice actually has a remarkably minor influence on the jet stream's behavior.
Oh, really?
Yeah. Their simulations indicate that the connection between a warming Arctic and atmospheric blocking those stuck weather systems accounts for only about 10% of the jet stream's natural variability.
Wow, just 10%. So hypothesis B points out that the jet stream is naturally chaotic, and blaming every extreme weather event on a warming Arctic kind of ignores historical baselines.
Yes, and there is compelling observational data contradicting the idea that the jet stream is systematically weakening. A major 2022 reanalysis that utilized commercial aircraft data suggested the North Atlantic jet stream has actually strengthened.
Strengthened. That totally flips the script.
It does. And perhaps the strongest anchor for hypothesis B comes from paleoclimatology. A vital 2021 study reconstructed the precise patterns of the jet stream over the past 12,050 years.
Let me guess, by analyzing deep Greenland ice cores.
Exactly. And this millennia-spanning dataset revealed that all the radical wobbles and extreme shifts we've observed in recent decades, well, they still fall completely within the normal range of natural historical variability.
Really? So it's not unprecedented yet?
Right. According to their models, the jet stream's behavior won't truly diverge from its natural historical patterns until the year 2060, even under high-emission scenarios.
That is fascinating. So we are actively living inside the data collection period of a massive planetary shift. Both sides observe the warming Arctic, both sides record the extreme weather, but definitively linking the two as cause and effect remains basically the holy grail of modern meteorology.
It absolutely is. And, just as we start to grasp the complexity of these high-altitude rivers, we realize the sky is filled with an entire multi-layered transit system of winds.
Oh, yeah, because it's not just a single highway up there.
Not at all. The polar and subtropical jets get all the attention, but the atmosphere is deeply stratified. High above the standard jet streams, in the upper stratosphere at a staggering 80,000 feet, you find the polar night jet.
The polar night jet? That sounds like something out of a sci-fi movie.
Doesn't it? It's a phenomenon that only exists during the dark winter months, the polar night. It races eastward at around 30 miles an hour, forming an incredibly high-altitude boundary that traps the coldest air inside the polar vortex.
And if we drop all the way down near the surface, we find a network of low-level jets dictated by the physical topography of the Earth itself.
Yeah, you have barrier jets that form when wind slams into mountain ranges, creating high-speed currents flowing parallel to the peaks.
And then you have those intense valley exit jets, which funnel air through deep mountain passes and shoot it out over adjacent plains at like 45 miles per hour.
And these local, low-level jets carry staggering global consequences. Take the low-level jet in Chad, Africa. It acts like an industrial sandblaster, lifting immense volumes of dust out of the Bodele Depression.
Wait, isn't that the most crucial source of atmospheric dust emission on the entire planet?
It is. This single wind current fuels that entire dust system.
Wow. And then you have the Somali jet ripping off the East African coast. It essentially acts as a massive atmospheric water pump, pulling moisture directly off the ocean to fuel the massive Asian monsoon system.
Add to that the African easterly jet, which drives the West African monsoon and simultaneously acts as the nursery for tropical waves.
Pushing these turbulent systems out over the warm Atlantic Ocean where they spin up into the hurricanes that eventually strike the Americas.
Exactly. The dust from Chad, the life-giving monsoons in Asia, the destructive hurricanes in Florida, they were all orchestrated by completely different tiers of this global jet stream network.
It's just massive, multi-layered global transit system. But the sheer physics of these atmospheric rivers are so fundamental, they aren't even confined to Earth, are they?
No, they aren't. Astrophysicists have detected distinct jet streams on Venus, Saturn, Uranus, Neptune, and most spectacularly, Jupiter.
Okay, wait, which raises an incredible mechanical question for me. We just established that Earth's jet streams are the product of the thermal wind relation, right? The intense solar heat at the equator versus the freezing poles.
Right.
But Jupiter is hundreds of millions of miles further from the sun. It receives a tiny fraction of the solar energy we do. So how does a freezing gas giant have the most intense, violent jet streams in our solar system?
It's a great question.
I mean, when you look at a photograph of Jupiter, those iconic swirling red and white banded colors, those are literally just massive visible jet streams. How are they powered without a hot equator?
That cuts to the absolute core of planetary physics. Because on Earth, our atmospheric rivers are entirely solar-powered by the sun's external radiation. But on massive gas giants like Jupiter, the solar heat is negligible.
So what's driving it?
Scientists conclude that Jupiter's jet streams are driven by the planet's internal heat.
Internal heat.
Yeah. Massive convection cells churning deep within Jupiter's liquid metallic core generate this intense thermal energy. That energy rises to the surface, hits the incredible rotational speed of the planet, and spins into those colossal bands of wind.
That is mind-blowing. So to recap, from the duration of your flight to the cost of your produce during a drought to the brutal cold of a polar vortex, your reality is shaped by these fast-flowing atmospheric rivers.
An invisible mechanism hypothesized by storm watchers, verified by volcanoes, and mapped by pilots fighting brutal headwinds.
Exactly. It really reveals how delicately balanced our climate engine truly is. But your answer about Jupiter's internal heat leaves us with a staggering thought experiment to close on.
Oh, I know where you're going with this.
Yeah, think about it. If Jupiter can generate continent-sized jet streams entirely from its own internal heat, completely independent of a star, imagine the weather systems on rogue planets.
Right, because there are countless planets out there that have been violently ejected from their solar systems.
Wandering through the pitch-black void of deep space without a sun, driven entirely by the dying embers of their own internal cores, they could possess entirely alien extreme forms of atmospheric rivers.
Invisible violent winds howling endlessly in the absolute dark.
An invisible river flowing in total darkness. That is something to keep you awake tonight. Thank you for joining us as we mapped out the skies. We will catch you on the next deep dive.